kick off the semester with Eric Sharpe from Virginia Tech. He's going to tell us about supergravity moduli spaces.
Well, thank you very much for the introduction. It's a pleasure to be here. Today what I'm really going to talk about is something called the Bagger-Witten line bundle over moduli spaces that arise in supergravity and also superconformal field theory. So this is some line bundle that was whose existence was originally noticed by Bagger-Witten, as I will review in a few minutes. The reason for my interest is really some work of Seiberg, Komarkovsky, and others who argued, in essence, that this Bagger-Witten line bundle is flat. And for a long time this bothered me, because the Bagger-Witten line bundle is the square root of something that sometimes has mathematical import called the Hodge line bundle over modulized spaces of CalabiYaus. And mathematicians thought they sort of understood the basics of Hodge line bundles, and the mathematicians I spoke to found that thing to be very, very surprising. To further complicate things, there were basically no examples that had been completely thought through. It turned out in hindsight there was one example we'd known, but people had sort of forgotten about and shouldn't have. But the upshot is that actually Seiberg and Zohar actually got it right. And there's some other interesting implications to what they're going or to what they did. So let me give you the executive summary of the talk. If you forget everything else I say today, let me recommend these two bits. So first, the Bagger-Witten line bundle on a moduli space of CalabiYaus, as would arise, for example, in a string compactification, has an intrinsic understanding as a line bundle of covariantly constant spinors. This is related to, but not quite the same thing as, the line bundle of holomorphic top forms. And I'll argue later in this talk that consistency of that statement is going to give a very simple, intuitive way of understanding this claim of Seiberg and Komarkovsky. To reconcile that claim with physics basically is going to require that the Bagger-Witten line bundle is flat, at least at some loose level. Second, it seems to be flat, and I'm going to conjecture that it is always non-trivial. And this seems to have some sort of relationship with various statements about existence of UV completions and the swamplands. So let's just say for the moment this has, say it has tension with various statements about the swampland. I'm not by any stretch of the imagination an expert on the swampland, but when I get there in my talk, I'll elaborate on what exactly I mean by that. I'll give you an outline of what I plan to do for the next hour. So first off, I want to begin by reviewing the Bagger-Witten line bundle. What was it that Bagger-Witten did? How does this arise in supergravity? How does it arise in string theory? What's this whole thing about? Next, I'm going to describe how the Bagger-Witten line bundle is, in the case that the moduli space in question is a moduli space of CalabiYaus, a line bundle of covariantly constant spinors. And I'll also tie that description into this result of Seiberg, Komarkovsky, and their various collaborators in the series of papers they wrote that claims the Bagger-Witten line bundle should be flat. Next, I will describe the results that, in examples, is flat but non-trivial. And then finally, because it's a bit more technical, at the end of the talk, going to discuss examples. In particular, what I really want to do is work through the simplest non-trivial example that I can build and walk through it at what I hope is going to be a fairly elementary level to give a very explicit discussion or a very explicit description of what in the world this thing really is when you try to build it concretely. And the example of a moduli space of elliptic curves. And why is it non-trivial? All right, so let me now begin with the heart of the talk with a review. So the Bagger-Witten line bundle, as the name suggests, first discovered by Bagger and Witten. So let me quickly work through what exactly they were doing. Now, Texas A&M is renowned as having a very strong supergravity group, so for many of the people in the audience, what I'm going to say next will be horribly boring. But I also see some much younger people in the audience, so this next part of the talk is really aimed at the younger people to help make certain that everyone is up to speed on these ideas. So, the basic idea of Bagger and Witten is as follows. In a rigidly supersymmetric theory, if I have a set of scalars whose vevs look like they're living on some Kähler moduli space, then across coordinate patches on that target Kähler moduli space, the theory is invariant under transformations of the Kähler potential, under which K goes to F plus F bar. So in rigid SUSY, the theory is invariant. And this is basically baked into the superspace description of a rigidly supersymmetric four-dimensional n equals 1 theory. The action looks like an integral d fork theta of the Kähler potential as a function of superfields, and then adding some holomorphic function or some anti-holomorphic function. Those just get annihilated by d fork theta. So in this particular superspace description, the theory is manifestly, necessarily invariant under that. Now, local supersymmetry is a bit more complicated. So in 4D n equals 1 local SUSY, it turns out that because of the manifold couplings of the theory is not invariant unless you combine that transformation of the Kähler potential with some phase rotations of the fermions. And let me look at my notes to try to get the signs right, because I'm always terrible at this. The gravitino will transform like the exponential of minus I over 2 times the imaginary part of that holomorphic function f. CalabiYau, the scalar superpartners, will transform like the exponential of plus I over 2 times the imaginary part of f chi I. If this is a gauge theory, then the gauginos will transform in a similar way. And then altogether, this combination of this action on the Kähler potential together with these phase rotations of the fermions will leave the theory invariant. So these phase rotations of the fermions end up defining a line bundle. Let me briefly outline how exactly that works. So first off, just a set notation, let me let U alpha be an open cover of whatever this supergravity moduli space is. This Kähler space of possible field vevs, let's assume it has some open cover by the U alphas, and then let F alpha beta be the holomorphic function arising on U alpha intersect U beta. Then on triple overlaps, for example, if I take the sum F alpha beta plus F bar alpha beta plus F beta gamma plus F bar beta gamma plus F gamma alpha plus F bar gamma alpha, that's going to be the same thing as K beta minus K alpha. The first two terms are just the difference between the Kähler potentials associated with each patch, plus similarly K gamma minus K beta, plus k alpha minus k gamma. And if you track through, see that k beta cancels out that one, that k alpha cancels out that one, that k gamma cancels out that one. So that whole sum is equal to 0, which means the sum f alpha beta plus f beta gamma plus f gamma alpha must be some pure imaginary function, given that f plus its complex conjugate is equal to 0, which we will denote h alpha beta gamma. And then on quadruple overlaps, you can argue similarly that the analogous combination of the h's is equal to 0. So explicitly h alpha beta gamma minus h alpha beta delta plus h alpha gamma delta minus h beta gamma delta is equal to 0. Now, if there is no gauge symmetry in this particular supergravity, if this is just an ordinary, how should I say, an ordinary four-dimensional n equals 1 supergravity, not coupled with any sort of gauge theories, you have a bunch of chiral superfields, but no gauginos floating around, then we can use those fermion transformation laws to further constrain possible f's and h's. For example, chi I gamma, the scalar superpartner I on patch U gamma, is related to the chi on beta by a phase. So I were to part f beta gamma chi I beta, but the chi on patch beta is related to the chi on patch alpha by a phase. So we can write this as the exponential of I over 2, imaginary part of f beta gamma times the exponential of I over 2, imaginary part of f alpha beta times chi alpha I. At the same time, instead of doing this in 2 steps, I could do this in 1 step. I can relate this to chi and alpha simply as exponential of I over 2, imaginary part of f alpha gamma, chi alpha I. And so putting that together, that means the phases all need to have a product that's equal to 1. So I over 2 times the, so I over 2 times the imaginary part of f beta gamma plus f alpha beta minus f alpha gamma has to be 2 pi I up to an integer, or has to be 0 up to an integer multiple of 2 pi I. So we can write this as 2 pi I n alpha beta gamma, where n is some integer. And since the sum of the f's is pure imaginary, its imaginary part is itself up to a factor of I to cancel out the i's. So this means that the exponential of I over 2 times the imaginary part of h alpha beta gamma is equal to 1, or that the h alpha beta gammas are, let's say, 4 pi I times n alpha beta gamma. And suffice it to say, if this is true, that ends up implying that the transition functions e to the minus f over 2 define an honest line bundle over that moduli space of scalars. If there's a gauge symmetry, this argument breaks down, but it doesn't break down too badly. It turns out that if there's a gauge symmetry, these h's are not constrained to be of this form, but they still have to close like this in quadruple overlaps. So instead of getting an honest bundle over that moduli space of scalars rising in supergravity theory, you get some sort of twisted or fractional bundle. For most purposes, it can be treated more or less the same way as a line bundle, and so I'm just going to refer to it as a line bundle and gloss over that distinction. And if anyone wants to hear more about it, I'm happy to do so after the talk is over. Okay. Now, there's some other bits and pieces. The super potential of the theory is also going to transform non-trivially under the Bagger-Witten line bundle. basically because of the Yukawa couplings, up to factors of turbines. The Yukawa couplings relate derivatives of the superpotential to the scalar superpartners. So in order for the resulting Yukawa coupling terms to be well defined, we have to require that the superpotential also transform or also be a section of this particular line bundle, which plays some meaningful role. Now, so far this is just how the Bagger-Witten line bundle arises in supergravity. It also arises in worldsheet supersymmetry. We can also see this structure directly on the worldsheet. And let me quickly review that, because to get the results I want is going to require jumping back and forth between these two different interpretations, between these two different roles of the Bagger-Witten line bundle. One is some line bundle over the supergravity moduli space, another as some structure arising in moduli spaces of two-dimensional superconformal field theories. It's that interplay that's going to be essential. So, Bagger-Witten also arises over moduli spaces of two-dimensional n=2 superconformal field theories. And all I really need is a chiral n=2 algebra. So I'm going to gloss over any distinction between 0-2 theories and 2-2 theories or other possibilities. It's just one copy of this n=2 algebra that's going to be relevant for what I have to say. So we have some moduli space of n=2 superconformal field theories. We can imagine two different patches on that moduli space. Within any one patch, I can use superconformal perturbation theory to deform one superconformal field theory to another. How are the theories on different patches related to one another? Well, in principle, across patches on the moduli space, the theories should be related by global symmetries. If I describe one of these conformal field theories by a set of operators, say, then when my possible transition functions as I move from patch to patch are going to involve acting on those operators with whatever global symmetries exist in theory to get the operators described on that different patch. Now, if I only allow myself to talk about n=2 superconformal field theories, then the only global symmetry I'm going to get to talk about will be a U1R symmetry inside the n=2 algebra. And then in more general cases, one can play more complicated games. I could imagine a 0,2 theory with a right moving n=2 structure and then some other global symmetries from the left movers. For simplicity, I'm not going to go there today, but certainly those permutations exist. Now, on triple overlaps, those transition functions defined by, in this case, the U1R global symmetries will close up to other symmetries. Essentially, much as we saw in the review of what Bagger and Witten originally did in four-dimensional n=1 theories. In the four-dimensional case, if there's no gauge symmetry, we get an honest line bundle. If there is some sort of gauge symmetry, the transition functions only close up to some h, which is determined by the gauge symmetry. And moreover, global symmetries in a two-dimensional theory are gauge symmetries in space-time. So the fact that here we have transition functions closing up to a gauge symmetry really is exactly the same thing as saying that in the two-dimensional superconformal field theory, transition functions only close up to other global symmetries, as those worldsheet global symmetries are going to define space-time gauge symmetries. So this really is the same story, just from a different perspective. Now, this setup has been described by others. Let me give you all a few more highlights on how they relate. A two-dimensional n=2 superconformal field theory has a special operator, a special class of operators called spectral flow operators, whose role is to change the boundary conditions in the two-dimensional theory, enable you to interpolate between two-dimensional Ramon boundary conditions and two-dimensional Nebel-Schwarz boundary conditions. And that means, in fact, that the spectral flow operators form an integral part of the vertex operator for the space-time supercharge. Because if I want to build spinors on the worldsheet, at least in an RNS worldsheet, the target space spinors live in a worldsheet Ramon sector. The target space bosons live in a worldsheet NS sector. So if I want to get target space supersymmetry, I need to relate the two of them, and spectral flow operators are how that's done. So there's a couple in particular that are worth pointing out. There's one I will denote, well, there's really a family of spectral flow operators denoted U theta, where theta simply characterizes how I twist the boundary conditions. There are two in particular that are particularly noteworthy. U1/2 rotates Ramon boundary conditions into Nebel-Schwarz boundary conditions and back and vice versa. So this is the operator that actually, this operator becomes a piece of the vertex operator for the space-time supercharge. So the existence of this operator is responsible for space-time supersymmetry. This operator is also closely related to the chiral Ramon vacuum, perhaps unsurprisingly, for reasons I will elaborate on later. And more to the point, when I try to work with these theories in families, when I build a family of two-dimensional superconformal field theories, these operators sort of glue together to form a line bundle. The bundle of U1/2s turns out to be the same as the Bagger-Witten line bundle, LBW. There's one other operator I should mention, for one other value of theta, the spectral flow operator is relevant. U1 rotates, well, it does this twice. So it's going to rotate, for example, in a four-dimensional n=1 chiral, but this operator will rotate a boson to a fermion to an auxiliary field. It'll basically do two U1/2s. It's U1/2 squared. These guys, in a CalabiYau compactification of string theory, correspond to the holomorphic top forms. And they have U1R charge plus or minus C/3, depending upon your conventions. U1R charge of these things, I should add, is at the same time plus or minus C/6. And the line bundle of these operators is a bundle I will denote by LH. It's the over a moduli space of CalabiYaus, it's the bundle of holomorphic top forms. Now, these two bundles are not unrelated, and you can sort of guess how this is going to go. These operators have charge, forgetting the signs for second, C/3. These operators have charge C/6. This operator is basically the square of this operator, so you probably won't be too surprised to hear that LH is the same as the tensor product of two copies of L Bagger-Witten. Yeah?
So this is also what they call the canonical line bundle?
Not in, no, that's a good guess. So this is the, it's the bundle of holomorphic top forms over the moduli space.
Oh, it's over the moduli space.
So,
it's not just one CalabiYau,
exactly.
but it's a moduli space over all the CalabiYaus. And
exactly.
on the moduli space, so what's a moduli space? Is a moduli space scalar, or I mean,
yes.
It should be scalar, right? Because
That's
we
right.
have a scalar
That's
potential.
Right. For example, we want to be able to see these things in four-dimensional n=1 supergravity, and then any moduli space we'll get there has to be scalar essentially as a consequence of supersymmetry.
But when it is scalar and the top form is is trivial, so the first Chern class vanishes, then it's
What?
CalabiYau.
But this is the moduli space of these things. So it's not the, for a CalabiYau, the canonical bundle is on a CalabiYau, the canonical bundle is necessarily trivializable. This isn't a CalabiYau. This is a moduli space of CalabiYaus. So the fibers look like holomorphic top forms, but when you put them together, they're not, this line bundle is not, a section of this bundle is not a holomorphic top form in a moduli
You
space.
say it's flat, but it's not trivial, right?
Yes.
That's your statement, so. I
That's
mean,
right.
okay.
And more to the point, the moduli spaces in general are not CalabiYau, and the, a section of this is not a holomorphic top form. Rather, if you evaluate, if you take a section and evaluate it at any one point in the moduli space, the result will be, over that CalabiYau, a choice of holomorphic top form. And then as I wander around, I'll get other holomorphic top forms. I might wander back to myself, I can get the same one with a phase. But there's no triviality constraint in constructing a moduli space of these things. But that's an excellent question because this can be confusing. So please do, bring them on. All right. So, so one consequence of this, let me mention as a quick consistency check, the space-time superpotential. So for the n equals 1, space-time superpotential W acts like a section of the Hodge line bundle. So here the space-time superpotential is a section of a bundle over the moduli space of possible scalar field vebs in that supergravity. This is from Bagger-Witten's original paper. If you just look at the Yukawa couplings of the supergravity theory and look at the phase transformations of the scalar superpartners, the gravitinium and so forth, then you find that this thing has to transform like, well, the tensor square of the Bagger-Witten line bundle, but I've told you that's the same as the Hodge line bundle. Note, or maybe recall, the Yukov-Waffa-Witten superpotential. So in a flux compactification, they have some elegant expression in which they write the four-dimensional n equals 1 superpotential with some integral over the CalabiYau of fluxes, I'll call G, wedged with the holomorphic top form. So from this whole picture, if the space-time superpotential is a section of this bundle I'm calling LH, then that means it's transforming in the same way across the moduli space as the holomorphic top form. And in the Yukov-Waffa-Witten description, that's more or less manifest because you see a copy of the holomorphic top form here. So as you wander around over the moduli space, if this thing gets phases, then whatever phases the holomorphic top form picks up, this thing should also pick up. So this is sort of a quick consistency check to see why it's consistent for the Bagger-Witten line bundle. For the superpotential to live inside that, you can sort of see that explicitly from that expression. Oh, no, thanks, but maybe later. Okay. Now, so far so good. Now I think I finally can address the first of those 2 points in the executive summary. So the first question I asked was, is there an intrinsic definition of this thing? So the reason I said this is because you might want to, or in my case, you certainly want to, go and ask a mathematician how to compute this thing, or what this thing is. And if you go to a mathematician and say, okay, what is this Bagger-Witten line bundle in any given case? And all you give them is this description that, well, if I take the Taylor potential and do this, then the Bagger-Witten line bundle has transition functions like this. They'll laugh at you. This is not a particularly useful definition for them. It's an observation. It's not something they can do any computations with. So for that first point on the executive summary, what is an intrinsic definition? What is something you can take to a mathematician and say, okay, how do I compute this? What is this thing? So to answer that question, I'm going to specialize to moduli spaces of CalabiYaus. So in principle, lots of different moduli spaces that could arise. Hang on just a second. So if I consider a heterotic compactification, a perturbative heterotic string compactification of 4-dimensional n equals 1 theory, the actual moduli space isn't only going to be a moduli space of CalabiYaus, it's also going to be a moduli space of bundles over that CalabiYau. The total structure is going to be much more complicated, and I can't give you an intrinsic definition for the general case. I don't even know what the most general case is. So I'm going to focus on a simple case, well, relatively simple, in which I can actually give you a sane answer to this question. And then for more complicated cases, well, those can be treated on a case-by-case basis. Yeah?
If the purpose is just to talk to a mathematician about what this is, why can't you take the square root of the bundle of outputs?
That's what I'm going to do eventually. Yeah, and that's what I'm going to do eventually. But they're still going to ask why. You can do that, and then the question is they'll ask is, why should I bother? Why should I care? What in the world is that describing? Why? What's so special about the square root?
The bottom one is famous, right? So it's not.
Yeah, this one is well, depending on who you talk to, this one is famous to mathematicians. LBW is well known for physicists. So I agree that one of these is famous. Which one depends on which group you go to. And the other group may not actually care at all about the other one of those two. So anyway, bear with me for a second while I describe this, because I think it's this will also give an intuitive understanding of claims that Maddie and Zohar were making. So we've already seen that LH is LBW squared. Now, let me make a couple of observations, and then I'll make a claim. So, let's recall how to construct spinors on a CalabiYau following actually Green, Schwartz, and Witten's text. This is an old construction. Let's start. To build any spinor on a CalabiYau, I can start with a covariantly constant spinor. There are two of them. Pick one. And I'm going to call it, let's say, capital Omega. And I'm going to treat it like the highest weight state in building a representation. Then, to get other spinors, I'm going to act by gamma matrices. So I'll have states like gamma I, omega, gamma ij, omega, and so forth and so on. And then finally, the lowest weight state in that representation is going to correspond to the other covariantly constant spinor. Now, some CalabiYaus will have more covariantly constant spinors, but on a generic CalabiYau of maximal holonomy, there'll be exactly 2. Now, the other one is basically going to be given by gamma top acting on omega. So, let me observe that if the omegas you can think of as coupling to the Bagger-Witten line bundle, then if I've done all the indices correctly, omega top, gamma top omega is going to couple to LH inverse tensor LBW. And yeah, that's right. And because this is supposed to couple to the, well, note further, that if if that second covariantly constant spinor, gamma top omega, also couples to LBW inverse, then we have the relationship, we recover the relationship. The square of the Bagger-Witten line bundle is the Hodge line bundle. There's more I can say, but let me use that to motivate the following claim. That LBW and LBW inverse are the line bundles of covariantly constant spinors. I expect the line bundle of the second, corresponding to the second one, to be the inverse of the line bundle corresponding to the first one. Let me make another observation about, point out something else about two-dimensional superconformal field theories. All from two-dimensional n equals 2 superconformal field theories, the structure of the space of chiroprimaries and Ramond vacua. So in an NS sector, the chiroprimaries typically line up on a line like so. If that's the conformal weight and that's the charge, then H is going to be Q over 2 the way I've drawn this. There will be chiroprimaries at various points along there, and the topmost chiroprimary will have charge given by C over 3. So in a two-dimensional superconformal field theory whose target is a CalabiYau, C over 3 is exactly the dimension of the CalabiYau. So we can identify this in some, well, we can identify this in fact with the holomorphic top form. And then more explicitly, the holomorphic top form can be written omega I to j, psi I, psi j. That's the actual chiroprimary corresponding to that one. Similarly, states in the Ramond sector, after we do spectral flow of the Ramond sector, we have a set of vacua that will all line up on a line. They all have the same conformal weight, which is C over 24, I believe. The largest charge is going to be C over 6. The smallest one is minus C over 6. Just as this state corresponds to the holomorphic top form, I claim that those two things, points I've marked with asterisks, correspond to covariantly constant spinors. More to the point, on a single CalabiYau, X. Going back to what Falk was saying earlier, the holomorphic top form is a section of the canonical bundle on X. The covariantly constant spinors, on the other hand, are sections of kx plus or minus the square root. So if the holomorphic top form is associated with an operator of charge C over 3, say, where C over 3 is the dimension of the CalabiYau, the two covariantly constant spinors are going to be associated with operators of plus or minus C over 6. They need to be represented in the space of Ramond vacua, and they should be the highest and lowest weight states. And looking on this picture here, well, the highest and lowest weight states in the space of Ramond vacua are the endpoints, which have exactly the right charges to be the covariantly constant spinors. And basically because of this diagram, again, we can say that if we identify these two things as the covariantly constant spinors, and we identify LBW and LBW inverse with covariantly constant spinors, then the action of spectral flow is basically to implement LBW squared is LH. So, in a nutshell, that's sort of a set of simple reasons to believe why this claim up here should be true. Let me also point out an implication of this claim. One of the nice things about this claim is it sheds some light on why the Bagger-Witten line bundle should be flat, which again is something that, well, I wouldn't expect the Hodge line bundle to be flat. Wouldn't have expected the Hodge line bundle to be flat. So, let's go back and think about consistency with the original Bagger-Witten description. So again, Bagger-Witten originally described this line bundle in terms of what happens as we cross between patches on the moduli space. The Kähler potential transforms like so. The fermions pick up phases like exponential of I resume imaginary part of F. Now, Bagger-Witten described one Bagger-Witten line bundle. In effect, what I've told you is that there are as many as the number of covariantly constant spinors. Now, how in the world can that be consistent? Well, not only are there as many as there are covariantly constant spinors, but they are inverses of one another. Now, there is a way that can work. Note, if there is a set of coordinates, a set of coordinate patches in which f bar is equal to minus f, then we naturally have two Bagger-Witten line bundles. Furthermore, well, let's see, f is a holomorphic function. If f bar is equal to minus f, that means f is pure imaginary. And if a holomorphic function is pure imaginary, that means f is constant, or at least locally constant. If the overlaps aren't connected, then it could be, it could take different value, it could take on different constant values on different components, but, so I don't want to just say constant, but let's call it locally constant. If the f's are locally constant, that means Bagger-Witten line bundle is flat. Now, this is by no stretch of the imagination a rigorous argument, but I point this out to give some intuitive understanding for how, in this context, at least of moduli space of CalabiYau's, Seiberg and Komargatsky's result, which I think I've since erased, Seiberg and Komargatsky's result makes more sense. They originally derived their claim by thinking very hard about the structure of supergravity theories. They wrote a paper looking at, or they wrote a few papers looking at coupling rigidly supersymmetric theories to supergravity. They looked at, they had a paper with Jeremy Gomez and Stefan Tyson and some others looking at worldsheet aspects. What happens if you try to carry through analogous manipulations? In the worldsheet, they had to work very hard, and they got this result after doing a tremendous amount of work. And my observation here is just that in the context of this claim, with a small amount of hand waving, there's a sort of natural intuition for what's going on. Hang on just a second, if the Bagger-Witten line bundle is really associated with covariantly constant spinors, there need to be multiple Bagger-Witten line bundles, and if the Bagger-Witten line bundle is flat, then you can actually, then there should exist coordinate patches in which you can make sense of that. Yeah.
Previously, you were pointing out that CalabiYau's can have more than two. For example, I guess you could have three things or something.
Exactly.
So what happens here with this? Naturally, we have two bundles. Then you would naturally have four.
Yeah. And for K3 cross T2, well, you can basically see how it's going to work. Let's talk about that later. But yeah, that's the.
But nothing goes wrong with the explanation.
Nothing goes wrong.
After this, there are two. Does it need to be two, or just at least two, or what is it?
At least two. So in the case of K3 cross T2, you have many more symmetries. The story becomes much more specialized. The moduli space for K3 cross T2 would actually be a product of two moduli spaces. So basically, you'd have a copy of the story on each factor in the product. Then the Bagger-Witten line bundle would really be a product of a Bagger-Witten line bundle on the K3 moduli space and a Bagger-Witten line bundle on the T2 moduli space. And then you get, from those two choices, you'd have a total of four. That's exactly the game you play. And again, this argument here is not meant to be rigorous. This is just meant to give some intuition for how in the world that claim over there can be consistent with Bagger-Witten's original claim, and also give some sort of insight into what Seiberg and Komargatsky were talking about in all those papers they wrote. Now, I'm running a bit short on time, there's a question. Oh, actually, let me point out one other thing and then pose a question to all of you. The other thing I want to point out is that this flatness result seems to be novel to mathematicians, or at least the mathematicians I talked to. They had not expected this, and this is why Ron and I is involved in writing a couple of papers on this.
May I ask quickly, is this related to GSO projection? It seems like you're
The
somehow
GSO
saying that
shows up.
there's a nice GSO projection.
GSO does show up. In principle, GSO information about GSO is buried in the worldsheet physics in here. In there, it's not. The statement really is that the statement I'd like to make is that both of the covariantly constant spinors should survive the GSO projection. Actually, the GSO projection is going to come back in a few minutes. Ask me again at the end of the talk. I don't know if I will answer your question, but I will certainly find a way to speak around it. So let me pose a question for all of you. So far, Bagger-Witten line bundle flat. I mean, I haven't given you any concrete examples yet. I'm going to do that in the last part of this talk. I'm going to work through the simplest concrete example that I can to illustrate what's really going on. I mean, when you actually have something concrete to work with. What we find in concrete examples is not only is the Bagger-Witten line bundle flat, it's also non-trivial. So this is something for which I have no good general argument, except that in the examples we managed to compute, it always turns out to be true. Furthermore, this is going to be true even for free field cases. And for this to be true in free field cases is a fairly, to me at least, is a fairly striking claim. We conjecture that both these statements are always true. And furthermore, I'm going to suggest this may give some sort of UV completeness criterion when applied to supergravity theories. Now this is, what I'm suggesting is related to, but a little bit different from some existing ones. So for example, I'm not an expert of the small plan, but I can read a few papers from time to time. One of Vafa's criterions for existence of UV completion is simply connectedness of the moduli space. And it's a fun fact that if I have a Kähler manifold, simply connectedness of, well, strictly speaking, a compactification of the moduli space, it's a fun fact that if I have a Kähler manifold that's simply connected, any flat line bundle is also trivial. Now here, the computations I'm doing are for moduli spaces that haven't yet been compactified, and furthermore they have some, what Seiberg would call Z-mod 2 one-form symmetries that really have to be stripped out in order to make sense of Vafa's statement. So there's no contradiction between these two statements, but it's left me feeling like I'm missing something. And since there are many experts in supergravity in the room, I'm going to pose you the question, what's going on? What am I missing? Is there a better way of thinking about both of these issues that ties them together and may shed some insight into either one? And I cannot answer this, but I would like to pose it. And that's one of the reasons I'm here today, basically to ask you all this question in the hope that maybe someone will have an idea or maybe ask me the right question that will sort of point the way to an answer. Okay, now in the 10 minutes I have remaining, let's see if I can show you a concrete example. I mean, I've walked my way, I've basically hand-waved my way through all these generalities about Bagger-Witten and Hodge line bundles. What I want to do next is show you concretely how all of this works in an explicit example, and I'll outline results for other examples where we've done computations. So the concrete example I want to walk through is a moduli space of elliptic curves. Because that, I think, is something we all know something about and can appreciate. Moduli space of elliptic curves. So, what's the moduli space of elliptic curves? Well, this is an answer everyone here knows. Let me describe it first as the upper half plane modulo PSL 2z. Now, I think probably everyone here knows the reason for the PSL 2z, but let me walk through it carefully anyway. If I take the complex structure parameter of an elliptic curve, and I should add this is the moduli space of complex structures. If I really build a physical conformal field theory, there'll also be a moduli space of Kähler structures, which looks the same. For simplicity, I'm going to focus just on the complex structures. So, the complex structure parameter, under the action of SL2z, transforms as A tau plus B over C tau plus D. And moreover, note that if I take the non-trivial diagonal element, this acts trivially on tau. And that's the reason we often describe the moduli space of elliptic curves in terms of a PSL2z quotient. Now, mathematicians actually don't. Mathematicians describe the moduli space in terms of an SL2z quotient. Let me describe one of the reasons they do so. Specifically, let me try to build a line bundle of holomorphic top forms. So, let's try to say fiber holomorphic top forms over that moduli space. Now, for an elliptic curve, holomorphic top forms are easy. If the complex coordinate is z, the holomorphic top form is just dz. It's not particularly deep. Holomorphic top form is dz. So all we need to do is figure out how dz transforms under SL2z. Now, you can show, well, in fact, it's known in the math community, the combination tau and z transforms as follows. Tau, as we've already reviewed, transforms like this, but z just picks up the denominator, not the numerator. So z maps to z over c tau plus d. That looks a little bit odd at first sight if you haven't seen this before, but it actually guarantees that just as this z has the identifications z plus n tau plus m, where n and m are integers, this rescaling means that this z transforms in the same way with respect to tau prime. So if I call this z prime, and I call that tau prime, then you can show that just as this z has these identifications, z prime has the identification z prime plus n tau prime plus m. And there are at least two special cases, if you haven't seen this before, you're likely to ask about. If z is equal to 1, that's one of the corners of the torus. If I construct the torus like so, here's 1, here's tau. If z is equal to 1, then under this map, 1 maps to 1 over c tau plus d. With a little bit of algebra, you can argue that that's the same as 1 minus c times a tau plus b over c tau plus d plus a minus 1. Since a, b, c into your integers, that's isomorphic to 1 under these identifications. And similarly, tau maps to tau over c tau plus d. But again, with algebra, this is the same thing as a tau plus b over c tau plus d plus d minus 1 times a tau plus b over c tau plus d minus b. And so again, that's isomorphic to a tau plus b over c tau plus d. So lo and behold, the mathematicians really do know what they're doing. Now, here comes the fun part. Tau is invariant under the center of SL2z. Z is not. Under the center of SL2Z, where in terms of this matrix here, this is C and this is D. C is equal to 0, D is equal to -1. So here, under that center of SL2Z, this term drops out, but D is -1, so Z goes to -Z. So, under that plus or minus 1 inside SL2Z, tau is invariant, but in particular dz is going to map to -dz. Well, z maps to -z, and dz is going to do the same thing. So, holomorphic top forms do not make sense over a PSL2Z quotient. To make sense of a line bundle of holomorphic top forms, we really have to work over an SL2Z quotient. So, to make sense of holomorphic top forms, well, one forms in this case, but I'm just going to keep saying top forms because I think that's the more useful way to think about it. To make sense of holomorphic top forms, we have to work on the upper half plane mod SL2Z. Now, the center of SL2Z still acts trivially on the upper half plane, but there's a mathematical construction, a mathematical generalization of spaces, which I'm not going to get into, which actually does keep track of these sorts of trivially acting Z2s. Essentially, you have a Z2 orbifold everywhere, and that having a Z2 orbifold everywhere is not the same as having no Z2 orbifold at all. The line bundle of holomorphic top forms makes sense over this thing with the extra Z2 orbifold everywhere. Or I'll phrase in more modern language, this space is an example of a space that has what Seiberg would call a Z mod 2 discrete one-form symmetry. If anyone here is into, I'm not seeing anyone nodding their head, so I'm guessing not. If anyone learns about one-form symmetries, this is a space with a discrete one-form symmetry. Now, that's what I do to make sense of holomorphic top forms, and this is one of the reasons why mathematicians talk about the moduli space of elliptic curves as this, rather than a PSL2Z quotient. Maybe not even the best reason, but it's one of the reasons why mathematicians talk about the moduli space in terms of SL2Z quotients. Now, in physics, we want more. And certainly we want to make sense of the holomorphic top form, because that's going to give us the bundle of those spectral flow operators U1. But we would also like to make sense of the bundle of spectral flow operators U1/2. So, makes sense of the bundle of U1/2s. And that's essentially the same thing as the bundle of chiral Ramond Fock vacuum. Now, how do these things transform? Well, if you spend a lot of time working with orbifolds, you can guess how the story is going to work. First off, there are really two such vacua, which I will call plus and minus. We're doing essentially free field theory. We have a free fermion, psi. There are multiple chiral Ramond vacua because we have a single complex fermion with periodic boundary conditions. Under a Z mod 2 that maps the fermion to minus itself, this is the superpartner to Z. Z picks up a sign under that Z mod 2 partner, hence its superpartner also picks up a sign. So these vacua are going to pick up a phase, like so. Now, the fact they pick up a phase, this is, in some ways, is a good thing. This phase doesn't square to 1, it squares to -1, but this reflects the fact that if I take a spinor in 4 dimensions and rotate it 360 degrees, it only comes back to itself up to a sign. This is essentially the worldsheet reason for that old Dirac rotation in a nutshell. More generally, under a more general action of SL2Z, on the target space elliptic curve, these fermions are going to transform like, sorry, not these fermions, these Fock vacua are going to transform like plus or minus the vacuum over the square root of C tau plus D. Now, the problem here basically is that plus or minus I squared is not equal to 1. It's equal to minus 1. So SL2Z does not have a well-defined action. So to get a space over which the Fock vacuum makes sense, we have to take another Z2 extension. To get a space over which the bundle of vacuum is defined, we need to replace SL2Z by a Z2 extension. Now that extension is known. Let me do this over here. The result is that that bundle lives on a quotient of the upper half plane by something called the metaplectic group. Never mind the details. MP2Z, the elements of MP2Z look like matrices and SL2Z together with a choice of square root of C tau plus D. We just write it as that. And there's a multiplication on that thing, believe it or not, that actually makes sense. The upshot is that basically because of these extra elements, that thing has a very natural action on these Fock vacua. So that line bundle of Fock vacua actually makes sense over this particular space. Let me now summarize some details of some final results. So, on upper half plane mod SL2Z, the group of line bundles, they actually do form a group under tensor products. I can multiply two line bundles. I can divide by line bundles. There's an inverse line bundle. That group turns out to be the Z mod 12. And LH generates Z mod 12. So in particular, LH is trivial. For the upper half plane mod MP2Z, the group of line bundles is Z mod 24. LBW is a generator of that Z24, and the square of LBW is the pullback of LH in a natural fashion. So LBW squared is equal to LH. Now I'm about 3 minutes over, so let me just quickly summarize results for a handful of other cases, point out the obvious, and then close. So that's elliptic curves. The Hodge line bundle or Bagger-Witten line bundle are non-trivial, but flat. They're flat because they just generate this finite group. Some other cases. Arthur Becker and some collaborators have suggested that in suitable flux compactifications, and I will provide details afterwards if asked, that they can get moduli spaces that look like the upper half plane modulo, for example, gamma 2. In this case, the group of line bundles is equal to Z4. The Hodge line bundle is equal to, the Hodge line bundle generates, and there's a similar story. To get the Bagger-Witten line bundle, we can replace that subgroup of SL2Z with a subgroup actually of the metaplectic group. We can pull back that subgroup to the metaplectic group. And again, we get a construction of the Bagger-Witten line bundle as some space with a Z mod 2 one-form symmetry relative to that one, and it has a property that LBW squared is LH. Toroidal orbifolds. Let's do some threefold examples. So we've looked at examples of the form T2 cross T2 cross T2 modulo some number of copies of Z2. There is a classification of orbifolds of this form by Tanagi and Wendland a number of years ago. Included in that list are some examples where the orbifold has exactly 3 complex structure moduli. So usually at a T6, the complex structure moduli won't just be copies of the complex modulus here, complex modulus here, and complex modulus here. They'll be able to mix with one another. So you actually get a lot more than 3 complex structure moduli. However, in special cases, you can imagine orbifolds that are only consistent with deforming this T2 or that T2 or that T2 with each one separately. So you have examples in which the number of complex structure moduli is only 3. You can perform the same analysis there. What you find is that the group of line bundles has infinitely many elements. Parts of it are freely generated, which means there exist non-flat line bundles over the moduli spaces of these things. However, the Hodge line bundle and the Bagger-Witten line bundle generate finite subgroups. So in particular, they're flat but non-trivial. So in all examples, well, there's one more set that's in progress. Ron Tanagi and Mark Maserato are, last time I heard, also looking at examples of Poisson-Barcia orbifolds, which are orbifolds of T2 cross K3. And for those Poisson-Barcia examples, again, LH, LBW are flat but non-trivial. I don't know of a general math claim, but I'm happy to make the conjecture that the Hodge line bundle and the Bagger-Witten line bundle, well, I think there are now a variety of arguments that they should be flat, though none of them come from mathematics, so we'll see how well those hold up over time. But I'm also happy to conjecture they're both non-trivial. And in fact, this is true now of every example we have computed or seen. All right, I'm now well over time, so I'm going to stop here and ask if anyone has any questions.
We have one question, and then we'll proceed with more questions afterwards. Yeah.
I cannot follow all the details.
That's quite all right.
Heavy-duty mathematics here going on, but the fact that you're dealing with global well-definedness of supergravity and equals supergravity